Hi everyone, good afternoon. My name is Woody Zhu. I'm currently assistant professor here at CMU from Heinz College. Very excited to be here. So this is a joint work with my collaborator from Harvard Business School, Michael Lee. And to begin with, I just wanted to give you some high-level ideas. So I'm kind of the researcher that works at the intersection between operations research, machine learning, and the statistics. And we have a broad interest in a wide variety of applications, including public health, transportation, emergency assistance. But nowadays, I tend to focus more on the similar challenges in the power system. And particularly, we're more interested in the decision-making problems in the high-stakes setting. So one of the examples is, if any one of you are from California, you must remember what has happened earlier this year. There's a wide range of wildfire in 2018, some of these wildfires are actually caused by the utility. Whenever there's like strong wind, the tree branches touch the power line, it will cause the fire, and then the fire develop into wildfire. And it literally makes the PG&E, which is the largest utility in California, go bankrupt. So what they wanted to understand is how they can strategically make some actions to mitigate the impact of the wildfire risk in response to those kind of extreme weather conditions. And one of the strategies is de-energize the power lines. So how do you do it? How do you de-energize the power line in a way that can minimize the risk while still make sure everybody get the power, right? So this is just give you some taste about what kind of problem that we're working at. So now I wanted to use another application as a motivating example. I have used this example many times. Probably some of you have know this example very well. So this is a collaborative project between, even when I was a PhD student, between Georgia Tech and the Atlanta Police Department way back in 2018. And that idea is we wanted to help those police officers to redesign the districting in the city, okay? Because the city is developing very, really fast. And the crime pattern is also evolving over time. So they wanted to adjust those districting plans in order to meet the demand. And more specifically, the objective is because this is the city of Atlanta, and you can see it consists of 6 different zones. And every single zone operate independently. So one of the objectives is they wanted to make sure that the police workload can be balanced across different zones. And the things that we can do is to tell them how to adjust those assignment of each one of these small geographic units, which is indicated by this gray, little area. So there are, if I remember correctly, 86 what they call the beat, the smaller geographic units, and they wanted to divide it into 6 different zones. Then how do we do it to ensure that the workload differences across the zone can be minimized? So this is like a typical predict and optimize problem, if you're familiar with the literature, where we need to forecast how much crime activity is going to have in the next 5-10 years. And then based on this forecast, we have to solve an optimization problem. So we have a paper about it. It has published like a while ago. And the idea is we first build a predictive model, like a simulation model, that is able to anticipate the crime pattern. And then we solve a mixed integer programming. And we basically just follow exactly what the police officers told us to do to set up the problem mathematically. And we solve the optimization. And this is what we proposed for the first time. And we spent so much time just telling those people, this is the best option you should take. This is the design that you should adopt. And this is my advisor by the time, was my advisor by the time. And she was literally presenting this design to Major John Quigley, who is in charge of this project. And John is, super nice guy. He said, wow, this is great. This is exactly what we wanted to have. And after rounds of discussion with other colleagues within the department, I said, well, unfortunately, Woody, I don't think this is going to work. And there are 2 major reasons. So one of these reasons is they're quite uncertain about the accuracy of the prediction, right? Because nobody can guarantee what's going to happen after that 5 or 10 years. And secondly, some people may suggest, well, even though I'm pretty sure this is going to be the optimal plan, but I don't think this plan is feasible. Because some of the design can cut off the access to the highway, and this community cannot be separated. So there are many other physical constraints. They don't, explicitly tell us at the beginning. So there's no way we can know those kind of information. So eventually, the way how we address this issue is, well, Woody, can you just rerun the model for multiple times, making sure that all of the designs look different from each other. So we can pick the one that we like. And this is exactly what we have done. So we rerun the model using heuristic optimization softwares like simple annealing, so that we are able to make sure that all the plans look slightly different from each other. And we presented 10 designs to the police chief, and they picked one that they liked the most. And it was implemented. It got approved in 2019, and it officially implemented later in that year. So what we can learn from this example? I've always thinking about this problem for a very, very long time. And I firmly believe there's some kind of principle behind the scene that we haven't had a chance to uncover. So the key challenge is there's a huge uncertainty in the human desirability, or to put it in another word, in the objective function, right? The original objective function proposed by the police, even though it was proposed by themselves, does not give us the full picture, right? So this uncertainty may stem from two things. So the first is the data insufficiency, right? We don't have enough data to give us the full picture. And secondly, we may have some misinformation. We may lack of certain covariates. We don't know certain constraints, or some of those knowledge can even hardly be formulated in a mathematical term. Okay. And if you circle back to the things that most of the consulting firms have done, usually these kind of high-stake decisions are made by a two-stage process. So first, usually the operational and analytical team is going to work together with the practitioner and offer a portfolio of multiple recommendations, right? And then the human decision maker is going to select the most desired option based on the preferences. If it doesn't work, you have to go back and redo the design again, and so on and so forth, until it reaches a point that everyone is happy. So I think this paradigm makes a lot of sense. So first of all, it addressed the incomplete information through the conversation between the designer and the decision maker. And secondly, because of the human are still holds the final agency. So naturally, humans are held accountable, so it meets the legal and ethical accountability constraints. And last but not least, sometimes we just love to have the human to be the decision maker. When you see a doctor, right, you wanted to see the real doctor. So the talk, in this research, we try to answer this question: can we solve this problem in the principal manner? So this is the basic pipeline for the decision, like a normal decision-making problem. And usually we start with the problem objective, and we wanted to give a model about it, so it can be regarded as a predicate and optimized problem. If the problem is risk-averse, then you can use other techniques such as robust optimization to find the most robust decisions that is insensitive to the risk. Here, one of the solutions, which is actually motivated by the example that I introduced, is we wanted to introduce human arbitration into the loop of decision making. And more specifically, we have two lines of the works that trying to tackle that complemented to each other but answer the same question. So the first is what we call recommend and select. Right? We wanted to recommend a bunch of solutions, and we give the human opportunity to make their selection. And the complementary framework is called the decide and validate, because usually we found humans love to make their own decision. And what we can do is to use the data to tell human, hey, how risky the decision is going to be. So these are two things, like two different line of works. Today we're going to mainly focus on the first one. But if you're interested, my student Wenbing is also among the audience. He also presenting our, the decide and validate line of the work here and in the poster session. So if you're interested, feel free to stop by his poster. So let's circle back to the police example. So one of the key challenges that we haven't fully addressed is the quantitative objective didn't tell us the full picture. Right? So let's assume the L is the human desirability. It's something we want to optimize for. And it consists of multiple things. Some of them are observable. Some of them are unobservable. And if you just take expectation over the things that we don't have as observation, then we can isolate the things that we have observation and the things we don't have observation. And if you just reorganize this mathematical equation, you will find something that looks very similar, just y plus u. So it's sort of like a model that has a noise term, right? So the y represents everything we know, like the typical objective function. And the u is something that we don't have observation at all. We have no idea what they wanted to have, but they exist. And if you simply regard the u, or which is the uncertain term, the uncertain component, this is the way how we solve optimization problem, right? We just optimize what we have known, and we find the optimal solution. This is the typical way how we address decision-making problems. And now let's see what kind of issue we might have with traditional methods. So this is the L, which is the red line, indicate the true objective that we wanted to optimize for. The orange line represents something that we have observed or something we artificially defined. And the blue line is something that we don't have the observation, but they exist there. So eventually we try to optimize this red curve. Unfortunately, we don't have observation, so we have to take a step back and optimize for the orange line. So this is set up. And if we just try to find optimal decision based on the orange line, you will find the green line, vertical line, will indicate the optimal decision. But if you look at the value of the red curve of the green line, it is actually suboptimal, right? So now let's re-examine the idea that I proposed earlier. What about we select multiple decisions? What's going to happen? So the high-level idea is we're trying to set up this kind of two-level like optimization problem to enable the collaboration between human and algorithm, where you have the inner optimization problem is solved by the human. Because like I said, we recommended M decisions and the human picked one they like, right? So the inner optimization problem is solved by the human. They pick the one out of M that they like the most, which maximizes the L, right? And outer optimization is something we wanted to solve. So the pi represents the solver, will represent any kind of stochastic generated policy. It could be generated model, it could be anything, it can be any kind of stochastic policy. So we wanted to find a policy that is able to recommend M decisions so that the likelihood of the people picking the one they like will be maximized, right? I hope that is clear. So we have a generative model that is able to recommend M decisions, and humans are going to pick one they like, and we wanted to maximize the chance to find their favorite decision. Here comes one of the key assumptions we have. This is the first assumption. We have to assume that a human can always make the best selection. Okay, this is something we have to bear with. Well, as everybody knows, humans always have a hard time articulate how good a decision is, right? If you ask, hey, can you give me a score? To quantify how good the decision is, it's almost impossible. But if you give two decisions to the human policymaker, then most likely they will be able to find which one is better based on their domain knowledge. And the selection itself reflects the way how human express their domain knowledge. All right? So now let's just express the L more explicitly by decomposing the L into Y and the U. And here comes our second assumptions, because U is a very general, unobserved zero-mean stochastic process. In order to operationalize this idea, unfortunately, we have to give it a structure so that we will have a better idea what does the property we might have for this optimization problem. So here, for simplicity, we assume it is a Gaussian process, which is quite common in the literature. And the Gaussian process, so the U can be modeled by a stationary Gaussian process with a mean zero and the covariance function K, which is quite important. I will talk about it later. So let's look at the main proposition we're going to have. So here, we can, with all of these assumptions, we can derive both upper bound and lower bound for this original objective function. And the one thing that's quite interesting is if M equals to, so both bounds contain the same term, and which is determined by the M. If M equals to 1, both terms go to 0. And it makes a lot of sense. If we don't give the option to human, then there's no point of adding additional information. We just optimize the Y, which is the quantitative objective. And the sigma is something what we call the variance that determines how certain or how uncertain you're about the objective. And the second term is the correlation that quantifies how diverse your policy is, which is super interesting. And the third thing is the sample impact, which is monotonically increasing over the M. If you have a larger M, if you give more option to the human, then you can less care about the Y because you have more opportunities, right? So here, because due to the time limit, I won't be able to go over all the details, but here this is a toy example. So the toy example is saying by constructing a very simple policy, what we call the epsilon optimal uniform policy, so that we can perfectly control the diversity of the policy and the optimality of the policy. As you can imagine, if the policy is wide, meaning it's more diverse, right? You're more likely to draw the samples that look different from each other. If it is narrow, it's more concentrated around the quantitative optimal. And if you look at the result, you can find a real interesting concave curve where you can see if the epsilon strikes somewhere in the middle, you will minimize the regret and also reduce uncertainty. So basically what we're trying to solve is to strike the balance between the optimality and diversity, okay? And one nice thing about the Gaussian process, because the Gaussian process is so nice, so that we can derive as a posterior. And assuming human prefers A1 over A2, then this posterior is actually analytically explicit, right? I don't want to bore you with all the mathematical detail, but just wanted to show the example. So if we don't have any feedback at all, it's going to be like a straight line with a very wide uncertainty band. If you just offer two options, it will take advantage of the information and just cover a little bit and also narrow the uncertainty. And as providing more information, you're going to be able to, reveal the true objective function more clearly. And to operationalize this idea, we propose two methods. One is for the continuous randomization. Basically, you can just train a genetic model that can produce solutions that is desirable to human. And secondly, it's designed for, it's kind of an iterative approach that is designed for the discrete optimization problem. And lastly, we have a lot of numerical results. We have shown our method compared to other baselines can attain the best performance in terms of regret. And also we apply this model to the police redistricting problem. And as you can see, when the sigma, which controls how uncertain you are about objective, when sigma is small, then you kind of heavily rely on the Y. So you don't see any differences at all across all the genetic samples. But as your uncertainty grows, you're going to see that the decisions look dramatically different from each other. Okay, and we also did the same comparative experiments using this data against other baseline, and we can prove that our model attained better performance. So to summarize, for the traditional approach, they simply just ignore the U and simply focus on the quantitative objective function by finding the single quantitative optimal solutions. Whereas in our framework, we're trying to find a policy that is able to produce multiple curated solutions to enable the interaction between human and algorithm or human and the data. And also the human selection can provide useful information to help us refine the understanding of the problem itself. And that concludes my talk. Thank you for your attention. Appreciate it.
Are there any questions for the speaker? Hey, really interesting talk. I appreciate you adding in this U to make the problem more realistic. Mm-hmm. I'm curious if you've thought about when either the environment is non-stationary or the human preferences are non-stationary and how that kind of
That's a great question, and there's no way we can do it, at least for now. I mean, we have to, at least for the type of the problem that we have been working on, I mean, the human knowledge certainly can override most of the decisions made by the algorithm. So we tend to believe that human is always correct. And one of the fun facts I can share with you is we have been working with a utility, and we have developed a really nice method and algorithms to deliver the decisions and present it to the utility companies until, our president candidate got shot. And we get the phone call early in the morning and say, hey, Woody, we have to redo the design. And I ask, why? I mean, everything has been approved by you guys, but why we have to redo it? And one of the reasons is because they're kind of pessimistic about the future of the renewable energy, and that will dramatically affect the design and all the details of the forecasting model. And it turns out they're correct. because of the BBB, the bill coming out, the company is under massive layoffs and the design, and we have to change the design dramatically. So I think that the example really highlights that sometimes the humans are correct about the decision they wanted to make, and this is something that the data or the algorithm will never be able to capture. So of course, for some application, we will not be able to always assume human is correct, and the human sometimes can be biased, and that's exactly what they're trying to resolve by extracting useful human information without introducing too much bias. But thank you for the question.
Let's thank our speaker one more time.